So we studied about the gaseous state, the states of matter, and today we will be studying about some crystalline solids. A solid is a solid, नजर आता है at room temperature it appears to be solid, but there might be different reasons for it to appear as a solid. Every solid is not identical in appearance, in properties, whether it's chemical or physical, and hence every solid can have a different structure. So today we'll study के solids जो solid नजर आते हैं, what might be the structure inside them. So the first thing that we will study is the giant ionic lattice, right? कोई चीज giant ionic lattice में अगर हमारे पास है, for example, sodium chloride is an example. Now, what is the structure inside sodium chloride? नजर तो हमें solid आ रहा है, sir. It is a salt, table salt test, sodium chloride. It appears to be solid at room temperature, but what is the actual structure inside it? Inside it consists of ions, which are just held together by strong electrostatic forces of attraction. If I zoom in, I'll get sodium ions surrounded by chloride ions, and every chloride ion is surrounded by sodium ion. Every sodium ion will have 6 chloride around it, right, left, upar, niche, aage, piche. And every chloride will have 6 sodium ions around it. So that is the structure inside is called a giant ionic lattice. Is this clear? So what does it have? It has charged particles, but those charged particles are in fixed places. They cannot move. Is this clear? So this is the basic structure of an ionic lattice. If I just expand the entire structure, if I zoom it in for you, this is how it appears to be. Is this clear? You've also studied this in O levels. Similarly, if I go for magnesium oxide, the structure is almost identical as sodium chloride. It's the same structure, but what is the difference in magnesium oxide? What ions are present in magnesium oxide? Oxygen is not an ion. O-2 ion is called oxide. So there is an oxide ion and a magnesium ion. So magnesium ion is a +2 and oxide ion is a -2. So the same structure, but now the ions have a +2 and -2 charge. So what will happen to the attraction between them? Sodium chloride may be attraction थी +1 -1 charge की attraction थी, that was kept keeping the entire solid together. तो उसमें भी हमारे पास +2 -2 की attraction होगी. So what comparison is there between the two attractions? किसमें? +2 and -2 attraction कम होगी ज्यादा होगी? ज्यादा होगी. +2 -2 attraction is far greater than +1 -1 attraction. So yes, magnesium ion is +2 ion and oxide ion is a -2 ion. Again, the structure is very similar, but this will be a rather stronger ionic lattice than sodium chloride. Both will have high melting and boiling points. Both will not conduct electricity in solid state, but will conduct electricity when the state is aqueous or molten. This will tend to have a higher melting and boiling point because of stronger attraction between the +2 and -2 ions. Is this clear? You have done these answers even in your O levels. Okay, now कुछ चीजें solid होती हैं, they are solid, but the structure is a bit different. अब हम example ले रहे हैं simple molecular. First example is iodine. Iodine tended to look like a solid. Yes, it is a solid. But once you zoom it in, उसमें वो ionic lattice तो नहीं है जो हमारे पास sodium chloride और magnesium chloride में था. Iodine just consists of I2 molecules. क्या होता है iodine के अंदर? I2 molecules होते हैं. The molecules are so big in themselves that they tend to be close together and they tend to look like a solid. What will be the intermolecular attraction in an iodine solid? कौन सी होगी? नाम क्या है? What is the intermolecular attraction? Van der Waals dispersion forces. क्योंकि iodine is a non-polar molecule. I2 एक I2 का molecule you can see, and there is another I2 molecule. अब there's नजर तो बहुत दूर से आ रहा है इस तरह से, but if you just zoom it well enough, you'll see that the particles are technically very close together. एक तो molecule इनका बहुत बड़ा है, so that increases the strength of the van der Waals dispersion forces or temporary dipole forces. वो इनकी बढ़ जाती है, स्ट्रॉन्गर होती है, मॉलिक्यूल का साइज बड़ा है तो ऑल द मॉलिक्यूल्स टेंड टू कम टुगेदर एंड इट अपीयर्स टू बी अ सॉलिड। है तो सॉलिड, लेकिन अंदर जाऊंगा तो अंदर का स्ट्रक्चर इज जस्ट सिंपल मॉलिक्यूल्स आर प्रेजेंट एंड नथिंग एल्स। इज दिस क्लियर? ओके, सो अगेन एक और एग्जांपल है बकमिंस्टर फुलरिन। इसको बकी बॉल भी कहा जाता है। इट अपीयर्स टू बी ग्रे ब्लैकिश सॉलिड सा नजर आता है। आप कहेंगे सर यू इट लुक लाइक कार्बन, इट इज टेक्निकली कार्बन, ब्लैक कार्बन सा आपको नजर आता है, ग्रेइश कार्बन, यू से सर इट इज सॉलिड। यस इट इज सॉलिड, but once you zoom well enough in buckyballs or buckminster fullerene, this is the structure that you tended to see. It is a big, not a big, it is a molecule which is made up of 60 carbon atoms. How many carbon atoms? 60 carbon atoms मिलकर इसका एक molecule बनाते हैं। तो वो आयोडीन वाली बात, एक individual molecule इतना बड़ा हो जाता है C60, तो other molecules tend to come together and this appears to be a solid. Is this clear or not? So this is a buckyball. It consists of hexagons and pentagons. सब कार्बन है, आपस में कोवेलेंटली बॉन्डेड है। buckyball और buckminster fullerene है टेक्निकली ये कार्बन ही, but it appears to be a solid and when you zoom it in तो आपको नजर आता है सॉलिड के अंदर तो बस कुछ नहीं, मॉलिक्यूल्स हैं। हाँ, the molecules are so big in themselves that they tend to have rather stronger van der Waals dispersion forces and the molecules are closer together, so it appears to be a solid. समझ आ रही है बात? है तो सॉलिड ही, बट देयर आर डिफरेंट रीजंस फॉर अ सॉलिड टू बी अ सॉलिड। इज दिस क्लियर? सो अगेन ये दो एग्जांपल्स अभी हमने की फॉर द स्ट्रक्चर इज सॉलिड बट द रीजन और द स्ट्रक्चर इनसाइड इज सिंपल मॉलिक्यूलर। और इससे पहले जो क्या था वो सॉलिड्स ही थे बट द स्ट्रक्चर इनसाइड वाज व्हाट वाज द बॉन्डिंग इन स्ट्रक्चर, दैट वाज आयनिक बॉन्डिंग वाज इन्वॉल्वड इन इट। ठीक है, अगेन इफ आई गिव यू एन एग्जांपल ऑफ आइस, आइस कैसे नजर आती है? हाउ वाटर is the state of ice, solid. And once you zoom it in, what do you see inside? You see molecules of water. Then how come it appears to molecule? तो इसके तो molecule भी छोटा सा है, इसके तो molecule का size भी बड़ा नहीं है. So why does it appear to be a solid? Because the intermolecular forces of attraction are strong. What kinds of intermolecular forces are in ice? Very good. Hydrogen bonding is present in ice. It's a very stronger intermolecular force. And when you may take the energy low enough, अगर आप इसकी energy कम कर दें तो फिर वो particles come together and due to the strong hydrogen bonding, it appears to be a solid. So अब जो basic हमने पढ़ा कि भाई if the forces are strong, particles करीब आएंगे और वो solid आपको लगेगा. Different reasons. पहले intermolecular forces हमारे पास can be van der Waals dispersion forces like in iodine or Buckminster fullerene, or the force can be a hydrogen bond like in ice. Is this clear? The common name for all intermolecular forces in your syllabus is van der Waals. Hydrogen bonding is also van der Waals. Temporary dipole is also van der Waals. Dispersion forces, your temporary dipole, or permanent dipole is also van der Waals. So van der Waals is a general name for intermolecular forces. There's different types of it. Is this clear? So these are simple molecular structures, but they appear to be solids. Is this clear? Why do they appear to be solids? Because they have rather stronger intermolecular forces. वो molecule का size भी बड़ा हो सकता है और the force itself can be strong like hydrogen bond. ठीक है? Is this clear? Now another reason for solids to be solid. Now we look at diamond. We have already studied two structures. Sodium chloride and magnesium oxide. हमने zoom in करके देखा when we figure out that it consists of ions that are held together by strong electrostatic force of attraction. Then iodine, Buckminster fullerene और ice को zoom in करके देखा तो उसके अंदर कोई ions वाइंस नहीं थे. They were just molecules held together by strong van der Waals forces, right? And the molecules were close together. When I zoom into diamond, a diamond does not have either of those structures. इसमें मॉलिक्यूल ही इतना बड़ा होता चला जाता है that the size of the molecule is so big we call it giant covalent or giant molecular. बात समझ आ रही है? तो the molecule बढ़ते the molecule tend to have a very huge structure and the huge structure of the molecule makes it appear like a solid. Is this clear? तो इसमें हम वैन डर वाल्स डिस्पर्शन की बात नहीं करते, हम कहते हैं मॉलिक्यूल इतना बड़ा है, द मॉलिक्यूल विद व्हाट आर द फोर्सेस दैट मेक्स अप अ मॉलिक्यूल. मॉलिक्यूल बनता है तो अंदर कौन सी फोर्सेस हैं? व्हाट काइंड ऑफ अ बॉन्ड इज बिटवीन द atoms which forms a molecule? Very good. Covalent bond is what forms the molecule, and covalent bond is a relatively strong bond. सही है ना? तो कोवेलेंट बॉन्ड की वजह से इट अपीयर्स टू बी अ सॉलिड. मॉलिक्यूल का साइज ही इतना बड़ा हो जाता है, एंड दैट इज व्हाई वी कॉल इट जायंट मॉलिक्यूलर और अ जायंट कोवेलेंट. बोथ नेम्स आर गिवन. दिस अगेन है ये सारे सॉलिड्स. नाउ देयर आर डिफरेंट स्ट्रक्चर्स प्रेजेंट इन दीस सॉलिड्स. इज दिस क्लियर? So this is a structure of diamond. Silicon SiO2 has a very similar structure. Silicon 4 oxide. Every silicon in that one, have a look at the diamond structure once again. Every carbon is bonded to 4 different carbons, and the next one is again bonded to 4 different and 4 different. So we tend to have this entire structure of diamond. Now similarly, if I go for silicon 4 oxide, every silicon is bonded to 4 oxygens, and every oxygen is bonded to 2 silicons. Have a look at it. Every silicon is bonded to 4 oxygens, and every oxygen is bonded to 2 silicons. The final empirical formula is SiO2, but this is the structure it tends to have. Again, ये बढ़ते 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 structure इतना बड़ा हो जाता है that the entire structure tends to look like a solid. The common name for this solid is sand. SiO2, silicon dioxide. Sand कैसे नजर आती है? How does sand appear? Liquid, gas, then it's a solid. And when you zoom it well enough, the molecule inside sand SiO2, the molecule itself is so big that it is actually held together by covalent bonds. Is this clear? It's called giant molecular. Again, another example of giant molecular is graphite. This again is another allotrope of carbon. There are hexagons. O levels में पढ़ा हुआ है. Hexagons are combined together. तो एक carbon तीन carbon से attached है. And then there are layers of hexagons, and in between the layers there is a layer of delocalized electrons. The graphite is one of the very few covalently bonded substances that tend to conduct electricity. इसमें भी again molecule का size hexagons बनते 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 beehive structure बनते बनते इतना बड़ा हो जाता है that one sheet of this graphite tends to become, graphene कहते हैं sheet को, this tends to become so big that ये पूरा एक molecule ही appear होता है, and we call it giant molecular. And it another आपको graphite बिल्कुल black powder की तरह नजर आए. Is this clear? So again, this is again a giant molecular structure. Is this clear till this point? Sorry? Delocalized electrons. O levels में पढ़ा है कि hexagonal layers होती है हमारे पास. Hexagon structure होता है beehive वाला, और ये layers of hexagon structures, and in between the stack of layers there is a layer of delocalized electrons, जिसकी वजह से graphite tends to conduct electricity. So we have gone through different solid crystalline structures. The first that we studied was giant ionic layer lattice. The second was simple molecular, and the third was giant covalent. एक और solid का structure है, that is metallic. Now when I look at the copper metal, जो मेरे घर में तार है, wire है, that tends to conduct electricity, it has neither of the 3 structures that we have studied. This is the 4th one, and this is called a metallic structure. How do metals tend to exist? Their outermost electrons is delocalized. तो सारे atom के outermost electrons delocalized हो जाते हैं, तो there is a sea of electrons and there are cations in it. And that is what the structure looks like. इसमें 8 coordinated की भी थोड़ी सी बात आती है कि every sodium 12 coordinated and 8 coordinated both are involved in it. So how does one atom has 6 neighboring atom touching it? Yes, this is a structure which will show you how does it happen. 1 2 3, there are 3 4 5 6. उसके ऊपर 3 इस तरह से, and उसके नीचे 3. So every atom is surrounded by 12 other atoms. So that is called 12 coordinated. ठीक है? Is this clear? इसलिए इनकी layers एक के ऊपर एक slide over करती हैं, इसलिए metals are ductile. पढ़ा होगा बचपन में science में. This is the reason for it. Now let's summarize all of them together. Let's talk about physical properties. Okay, giant सबकी physical properties एक एक करके देखते हैं. Well, let's have a look at the giant ionic. Their melting point is high. Sodium fluoride and magnesium oxide are examples. Magnesium oxide तो बकायदा is used in the lining of furnace where you melt metals. जहाँ आप iron melt करते हैं उसकी layering करने के लिए, उस furnace की layering के लिए magnesium oxide use होता था. Imagine उसका melting और boiling point कितना high होगा. So they have high melting and boiling points. Again, in order to conduct electricity, we need moving charged particles. We need particles that can move and that are charged. Giant ionic structure, we have charged particles, but in solid state, can they move? That is why it does not conduct electricity when it's solid, but once you dissolve it or once you melt it, now the same charged particles can also move. So they are moving and they were already charged, so that's why it conducts electricity in liquid or active state. Is this clear? And solubility, they generally tend to dissolve in water. Yes, there are many salts ionically bonded with them, but they do not dissolve in water. Or insoluble salts वगैरह कहलाते हैं. That's a detail for some time else. Right now we are just generally पढ़ने dissolve होते हैं, कुछ नहीं भी होते. Okay, what about simple molecular? Iodine example I gave you. In biology you would have also studied iodine vapors. हमारे पास बन जाते हैं. Iodine को जरा सा heat करो उसके vapors बन जाते हैं. That means इसका boiling point and melting point is not high, it is moderate. It will not conduct electricity in any case, whether you take the example of pure water, whether you take the example of Buckminster fullerene, whether you take the example of iodine, just liquid kar lo, you take it to any state possible, it will not conduct electricity because it does not have charged particles. अब आप move उनको कितना ही करते हैं, as long as they are not charged, there are no charged particles. Moving charged particles are needed to conduct electricity. इसमें charged ही नहीं है, no matter how much I move them, electricity will not be conducted. And generally ये पानी में भी आसानी से dissolve नहीं होते हैं. वो बात की डिटेल है कि कुछ हो जाते हैं तो फिर हम अभी comment नहीं करें. Now giant molecular, just the example, diamond, sand, silicon oxide, they also tend to have very high melting and boiling point. They do not tend to conduct electricity. Graphite is the only one that conducts electricity. When a silicon dioxide and diamond, they do not conduct electricity. Pani mein bhi, they do not tend to dissolve easily. Now that clear? Okay. Then we have fourth one, which is giant metallic. Copper example hai, sodium. They tend to have high melting and boiling points. And copper is a solid in all the wires that we have at home, right? Does it conduct electricity when it's solid? Yes, it does. Why? What moving charged particle does it have? Very good. The delocalized, the sea of electrons that we call it. Those are the electrons. They are there. It's a sea. The electrons can move around. They are not fixed in a certain position, and they are already charged particles. So there is a moving charged particle which makes sure that metals conduct electricity in all states. अगर मैं liquid कर लूँ तो भी conduct करेगा, obviously फिर और अच्छी करेगा, and so on. Metals, many metals tend to react with water. तो उसमें dissolving की बात नहीं आएगी, सही है? So if a metal is reacting with water, then that's a different thing altogether. So that is it for the basic structures of magnesium. React करता है शुरू में, but it forms magnesium hydroxide, and that creates a layer around the magnesium. It inhibits the entire magnesium to react with the remaining water. The magnesium, if you put powder of magnesium, that will entirely react with water.